Yeah, I'll try to be complementary with respect to the Andreas presentation. So the topic is going to be still at MAC and layer. So then I guess Carlos will go through the upper layers. So first of all, yeah, you have the outline of the presentation. We'll start by introducing the motivation for the joint RAN and backhaul optimization. Then I will explain mainly the key concept of this joint RAN and backhaul optimization. I will give you some detail on a solution that exploit this concept, and in particular I will present in details joint RAN and backhaul discontinuous transmission. Then I will conclude the presentation. So first of all, to start, maybe I can recall the two architectures that are used now in the cellular network. On the left, you have this classic distributed RAN, where standard eNodes B provide radio access to the end user, and these are connected to the core network through a heterogeneous backhaul solution that is also used to permit eNodes B to communicate each other and having some coordinated mobilities or intercell interference coordination. Then on the right you have the more advanced centralized RAN architecture, where you have only radiating elements providing these access functionalities, and on these radiating elements are connected to a baseband unit pulled through a fronthaul that implement where all the physical layer and MAC layer and so on, all the protocol stack basically functionalities are implemented. And this option then permit the connection on the baseband unit to the core network through the backhaul, through a classic backhaul. So distributed RAN has some well-known disadvantages in terms of intercell interference, energy consumption, also some problem due to the acquisition of the site for the eNodes B deployments. On the other way, this is a simpler architecture and also can use a heterogeneous type of backhaul solution that means lower cost. On the other way, centralized RAN provides centralization gain. We have already talked a little bit about that. So in terms of optimization for energy consumption, higher throughput, computational gains, and this permit the system to be more efficient. On the other way, it needs low latency, high capacity fronthaul, so like somehow fiber-like fronthaul, and this means larger investments for the operators. So in the iJOIN concept is somehow between these two architecture. So this flexible architecture, cloud RAN, and in this case, backhaul fronthaul is a key issue to design this new architecture. So why? So this table here has been somehow already presented by Andreas. Basically, backhaul set very stringent constraints in terms of capacity and latency. These constraints are related to the backhaul technologies and also to the topology that is used by the operator. In particular, the lower layer functionalities in the RAN are affected by latency and capacity constraints, very stringent constraints due to data plane functionalities, and upper layer, on the contrary, are mainly affected by latency issues, but these are quite more relaxed than for the RAN lower layer functionalities. So as Andreas has stressed before, you can see that there are some technologies that provide very quick connection. So latency is around microseconds range, up to 35 milliseconds. And also in terms of throughput, you have multi-gigabit technologies and technology like XDSL, where the capacity goes between 10 megabits up to 100 megabits per second. So from one side, we have seen that RAN and backhaul, they are interdependent. They add constraint. You have RAN constraint on the backhaul functionalities and backhaul constraint on the RAN functionalities. On the other way, the 3GPP considered that the backhaul network that support the RAN network is out of scope of the standardization. But we think that 5G will require this joint RAN and backhaul optimization to have a new, more flexible and more scalable architecture. So the co-design of these functionalities is required and has to take into account requirement and constraint from both the RAN and the backhaul network. So from our vision, there are two main ways to do this, to implement this concept. Or you can have RAN functionalities or backhaul functionalities that take into account their counterpart constraint, or you can design brand new functionalities that go across these two networks and are more performing. Anyway, you have to define new interface and functionalities to enable this interworking. So first of all, I will give you some detail on functions that are take into account the backhaul or the RAN constraint to improve the system performance. So one option that has been implemented in the iJOIN, in particular from Richard, is this hierarchical multi-stage scheduling, where the classic cooperating IC-IC scheme used to improve the network throughput, so in the central unit, but this the decision taken into account by this centralized IC-IC scheme are adapted locally at the node B to take into account of the backhaul latency delay that affect the CSI reliability. Another option is this centralized connection control scheme, where the cell selection is optimized by taking into account jointly the cell load, but also the backhaul capacity. So this solution can improve the area throughput in the network, especially when you have a low capacity backhaul, but also the overall utilization efficiency of the resource of the RAN, but also the backhaul network. So on the other way, you have some new functionality that has been designed in iJOIN, where classic functionalities are designed across these two networks. So you may have some joint RAN and backhaul error correcting scheme design that take into account the backhaul and the RAN fading to design coding and encoding scheme that reduce the complexity and latency while matching the packet rate target. Another option that is coherent with this approach is a network-wide energy optimization, where functionalities that reduce both the energy consumption at the RAN and the backhaul are used through switching on and off nodes in these two networks by adapting the network configuration, the overall network configuration, to the slow and fast variation in the traffic. So now I will give you some more detail on the scheme that we have provided in iJOIN. So it's in the framework of this network-wide energy optimization. So first of all, the backhaul has a larger impact on the overall network energy consumption. So if you have a look at these two pictures that show the small cell power consumption with respect to its load, as well as the power consumption of the backhaul with respect to the small cell load, you can see that the ratio between these two power consumption is very low. So just optimizing the energy consumption of the system, taking only into account the small cell power consumption, is not going to provide to you a lot of benefits. So the overall power consumption is due to the backhaul contribution plus the small cell contribution, and this can be easily represented by this linear model here, where you have the small cell power consumption due to some static power consumption plus a term that depends on the cell load if the small cell is active, or you may have some lower power consumption if you are capable to put this small cell in some idle mode. And the same way at the backhaul, you have some contribution that is due to the link between the small cell and the neighboring elements, and to the number of antennas that are used at the small cell for the backhaul, plus the contribution of the switches at the small cell. They aggregate the different backhaul links, or so if the small cell is active, or some lower consumption if the backhaul can put idle. So in our idea, we wanted to optimize the network configuration to the fast variation of the traffic, so at the packet level, at the millisecond level. So to support these functionalities, you need to have some hardware that at both the backhaul and the small cell is kept active. This is required to enable fast activation and deactivation of the small cell, but also to support some vital functionalities, some like synchronization or transmission of reference symbol. So furthermore, you can store the data received in the central unit and decide when to transmit according to the quality of service constraint. So this is based on the trade-off between latency and energy saving. The important point is to minimize the energy consumption while to avoid quality of experience losses at the end user. So the idea was to having a strategy that permit to the operator to decide when to transmit data and when to continue to sleep. That strategy, find this strategy is quite complex because the environment in which the network is working is stochastic. You have packet arrival and fading, interference. These are random variables. And also describing the network status is quite complex because you have many variables. Buffer status, the time to leave of the packets, cell capacity, loads, and so on. And there is a very large size of the space of these variables. So a first approach to find this strategy that permitted to decide when to transmit, when to buffer data is based on Q-learning. Q-learning is a reinforcement learning technique based on the Q function. This is a state value function that describes a discounted cost, the expected discounted cost of taking a given action A at a certain state S, and then following the strategy P, the policies P. So in this function here, R is a cost function that has to take into account the energy consumption and the packet losses, the quality of experience. Gamma is a discount factor that weights the impact of the future decision on momentary performance. So our problem was to find the strategy P that minimize these functionalities, where this is a multi-objective problem because, as I said, we take into account both the power consumption and the packet losses, and beta can be used to trade off amongst these two metrics. So the idea of Q-learning is try to learn this optimal policy by interacting with the environment. So there is some trade-off between exploitation and exploration. This means that you, from one side, you want to exploit the information that you have already acquired in the past to add some much gain as you can. From other side, you need to explore new strategy to having more knowledge about your environment and maybe knowing additional beneficial strategy. So this scheme here, this table here represents basically the main idea of the Q-learning algorithm. So you initialize this state value function arbitrarily, and then at each time step you choose an action, you observe the environment that changed, you receive some feedback from this change of the cost of your action, you update the state value function, and then it goes on until you have some convergence. So the problem here that find this optimal strategy is quite complex, because in our problem the number of state action pairs is very, very high, and this means that you have a very high requirement in terms of memory, but also the learning time is very long, and this is not acceptable. So the idea was to use some fuzzy logic to reduce the complexity of this problem. So in a fuzzy logic, you use some linguistic term to replace, to describe the variable of your problem. For instance, this linguistic term can be like small and large. So in our case, if you have variables that want to describe the buffer status, the cell capacity, the quality of service, for instance, for the buffer and the capacity, you can just say, okay, the capacity of the cell is very low, is low, is high. You don't need to tell, okay, the capacity of the cell is 50 megabit per second, 70, 80, 90, and so on. And also for the latency of this packet, you can just say, okay, the traffic, the buffer is urgent, is not urgent, it's moderately urgent, and so on. And you just use some membership function that match between the latency requirement and this linguistic term. In this way, the number of action and action value, action state pairs that you have to visit is very low, become very low, and you can quickly find the optimal strategy. So here you have some message sequencers that show how this algorithm can be implemented in our architecture. So here you have the virtual inode B composed by the small cell, some transport node, and the RAN as a service. And this virtual inode B receives information from the UE concerning the RAN status, RAN measurements like SNIR, reference senior received power, CQI, and so on, but also receive information by this network controller that measures the status of the backhaul, for instance, the latency of the backhaul or its capacity. So these information are jointly used at the RAN as a service to take this decision about switching on and off the link concerning the RAN and the backhaul. So after this decision, the RAN as a service has to implement some signaling procedure to activate or deactivate this link, and then it can forward data toward the small cell that has to implement the final resource management procedures. So here we have some results regarding this fast discontinuous transmission and the backhaul and RAN as a service. As Peter said before, you have several metrics that are used in the literature for the energy efficiency. And here we have selected one that is taking into account jointly the energy consumption of the backhaul and the RAN, but also the information bit that are transmitted in the network. So it's a joule per bit metric. We measured this metric in a very dense small cell deployment where users are requiring near real-time video traffic. And we compared 4 solutions. One solution is baseline where you don't have discontinuous transmission. One where you have discontinuous transmission but only at the inode B. One that considers discontinuous transmission jointly on the backhaul and the small cell. And the last one that takes into account these machine learning technologies. As you can see, if you do not consider the backhaul in the game, your gains are very, very limited. It's basically nothing. But when just considering the backhaul, when introducing the backhaul, you can have very important gain, especially in lightly loaded scenario, okay? But then, if you exploit this machine learning solution, you can profit of additional 45 gains in terms of energy efficiency. So to conclude this presentation, we have seen that joint RAN and backhaul optimization is a new paradigm that permit a new flexible architecture. It improved the system performance in terms of utilization efficiency, lower capital expenditure. It enables and supports this adaptive functional split. And you have these two ways to implement this joint RAN and backhaul functionalities. And in iJOIN, we have produced many results that follow this key concept. In particular, I invite you to have a look at the Jens demo where joint conning for accent and frontal is implemented. So concerning open challenges, from my perspective, we still need to understand this trade-off between backhaul and frontal, especially how to deploy optimal momentary backhaul links, while to enable flexible deployment for future requirements is a challenge. Also, in terms of standardization, this joint RAN and backhaul, it's an open point. And for the future, wireless systems are becoming more and more complex and more heterogeneous. So it's important, Peter has talked before about stochastic geometry, fuzzy learning, can be a very good solution that permit to understand how this complex system work and optimize them. And that's all.
Thank you, Antonio. The first really technical presentation. Any questions from the audience?
Yeah.
Do you recommend usually an adaptive functional split according to your instantaneous backhauling capabilities? Did I understand this right? Or?
So in general, or
Your approach.
so in my approach, actually, you can have several benefits. The idea of the flexible functional split is that you adapt the functional split to the backhaul constraint, but also to the RAN requirements. So, for instance, if the latency of your backhaul is quite high, here you can have you can implement only upper layer functionalities where you just decide to switch on and off links and backhaul links and small cell.
This I understood.
Yeah.
But do you expect that your backhauling status changes dramatically because you are using the different paths or in the backhaul, or do you more see it as a kind of static condition?
So I guess that the backhaul can change for sure due to if you have wireless link, maybe due to some shadowing problem.
Yeah,
but
does it change dynamically? This is
no.
This is not your okay. This is I want to make clear.
But I think the question goes in the direction on what time scale would, if you do change the function split, on what time scale, right? And I think so. Both in Antonio's work as well as I think in iJOIN there's a consensus. You wouldn't do it on a second or minute basis, but rather daytime would be the most that you would choose. And it's actually in D53 there's an own part on exactly this. What does it particularly in cost sense? Because if you would have a base station that allows you for a fully distributed operation and a fully centralized operation, it would be a super expensive base station. And one of the advantages that we do investigate is that we want to have a spatial flexibility. That means there's one small cell with an optical cable, then we have base station type A, and then we have a wireless backhaul, and we have a base station type B. And in the end, you may have like at most 2, 3 different kinds of base stations then.
Thomas?
If you consider co-location of different air interfaces or access points
Yeah.
in one area, what's the impact if you share the backhaul? I mean, you won't bring up 3 backhols for 3 air interfaces, but on these 3 air interfaces you might have different splits on the physical layer. And I could expect that this is really, on one hand, in terms of statistical multiplexing, there are opportunities, but if you have stringent latency requirements at the same time for another air interface, this might be a hurdle or a blocking point.
Yeah, I guess that
A Wi-Fi access point and a fronthaul on the same backhaul or on the same link.
Hopefully X-haul, right?
For sure, you will adapt the functional split. I guess the lower functional split would be adapted to the backhaul latency constraint and capacity. Then maybe for some RAT, you may have different functional split, as you said, but the lowest one will depend on these constraints.
So, Andreas, you can do last question.
I have a technical question because I like this result so much. Can you go
To this one?
Yeah, this one. So why is the cell DTX does really not show much gain or no DTX?
So, yeah, basically, this is due to the power consumption assumption on the small cell side and the backhaul side. Okay, here we assume microwave backhaul. So maybe for different technologies you may have some different trend, but anyhow, I guess that the ratio then will be more or less the same. And basically, you can see that the backhaul power consumption contribution to the overall power consumption is much larger than the small cell power consumption. For the small cell, the power consumption doesn't vary a lot according to with respect to the cell load, and it's around 15 to 20 watt. On the other way, for the backhaul, it's much more. It's 6-7 times more.
Okay, understood.
Probably very complex energy consumption model.
Did you assume here that you have the baseband processing within the small cell and the remote local side for this power? Here in the small cell, you have application of baseband processing and RF output power you consume for the amplifier. It's a different one as in a micro cell.
Yeah. So here I'm considering picocell. Okay, so according to the type of small cell that you consider, you have different power consumption model. So this number here comes from the EARTH project that has been finished a few years back. But then here I've considered that since I consider very upper layer functional split, the most of the functionalities are implemented at the small cell. But then, driven by Dario, in iJOIN project, we have considered a power consumption model where the functional split impact on the small cell, on the backhaul, and on the RAN as a service power consumption is taken into account.
All right. Thank you, Andrew.
You're welcome.